2.3 Objective 3. The student will be able to solve applications of quadratic functions. A Macon, Georgia peach orchard farmer now has 20 trees per acre. Each tree produces, on the average, 300 peaches. For each additional tree that the farmer plants, the number of peaches per tree is reduced by 10. How many more trees should the farmer plant to achieve the maximum yield of peaches? And what is the maximum yield? So apparently they're telling us that the optimal usage of an acre is to have more than 20 trees. How many more trees should the farmer plant? And so we need to find how many trees that is. Well, the yield, of course, will be the number of peaches per tree times the number of trees. And if you just think about, some of the possibilities, which I encourage you to do that, actually to write down, some different scenarios and get some data, and get your mind going with those. Right now, it's 300 peaches times 20 trees, 6,000 peaches. Plant one more tree and you have to subtract 10 the peach production per tree, but then you add one tree. So it's 290 times 21, and your total output goes up 90 to 6,090 peaches. So that's definitely something you want to do. What if you go 2 more? If you go 2 more, then your peaches per tree goes down 20, 2 times 10, because it says for each additional tree that the farmer plants, the number of peaches is reduced by 10. So it's only 280, but you have more trees, 22 trees, and the total number of peaches then is going to be greater, 6160. Okay, so if we define x to be the number of trees above 20. Number of trees above 20. Then you can see the pattern here. Okay, we could even make like an XY chart. An X XY chart where in the first case x is 0, and so for x equal to 0, the y value is 6,000 peaches, right? Because we had the this is 300 minus 0 times 10. Times 20 plus 0. So we weren't subtracting anything from the 300, we weren't adding anything to the 20. And so what I'm doing here is looking at these numbers. So 300 minus 0 times 10 times 20 plus 0 is what I'm talking about. And why am I doing that? Well, I want you to see the pattern as we go from x equals 0 to x equals 1 to x equals 2. Okay, as we make this xy chart. When x is 1, we've seen what happens. There's 1. That's how that 1 fits into the pattern. And here, looks bad. So we got a 1, we've got a 1. In the next one, we've got x equals 2 and a 2 and a 2. And so we can see the pattern now. When x was 0, we had a 0 and a 0. And now let's generalize to x. What if you had x? Well, then the yield will be 300 minus x times 10 times 20 plus x. Okay? And that is going to be a function for the yield in terms of x, which we're going to use to figure out what is the best x to use. And when you do that, how many peaches do you get out of it? What's the yield, right? Because that's the question. Well, there are two questions. How many more trees? In other words, what's x? And what is the maximum yield? So when you pick that x, what's the output? So as we have done, we're going to let x represent the number of additional trees. And we've derived the formula for yield. Now if you simplify it, you're going to get this trinomial, negative 10x squared plus 100x plus 6,000, right? Because if you FOIL it, there's your 6,000, and you've got a 300x minus 200x, that's 100x, and your leading term is negative 10x squared. So we've got this yield formula. To find the maximum yield, note that this function is quadratic. The graph is a parabola opening downward. The number, hence the vertex of the function will be the maximum value of the yield. Okay, we see a vertex, we kind of imagine a vertex right there. And so we do what we do with quadratic functions. Graph is below with the y value in thousands. We can get an idea of what we think that number is by counting the tick marks. 1, 2, 3, 4, 5, 6, and then 7. Looks like it's above it. But Now we're going to go to the algebra. Okay. We're going to complete the square to find the vertex of the parabola. And for negative 10x squared plus 100x plus 6,000. To complete the square, of course, you have to have lead coefficient 1. And we have lead coefficient negative 10. So we're going to factor out a negative 10 out of the first two terms, if you remember the method of completing the square. So we're going to put this in vertex form, and then we'll be able to say what the vertex is. Factor out a negative 10, x squared minus 10x, that's 6,000, not 600, plus 6,000. That's the same thing as our yield function, which is a function of x. That's why they say y of x. You can see that if you distribute the negative 10 over here, you do get what we got on the previous slide, negative 10x squared plus 100x plus 6,000, because it would be negative 10x squared plus 100x plus 6,000. Now to complete the square, we have to add the square of b over 2 on the inside, right? Where b is this negative 10. B is this negative 10. That's b. So b is negative 10. The square of b over 2 is the square of negative 10 over 2. That's equals, which is the square of negative 5 or 25. This 25 right here. That completes the square. That makes the inside of the parentheses a perfect square trinomial, which we'll be able to factor, and then that'll help us get vertex form. But when you add 25 on the inside, what are you doing? You're really adding, because of the negative 10 on the outside, that's really negative 250. And we have to make up for it by adding 250 on the outside. Now, remember that you should remember this formula. When you have x plus x squared plus bx plus the square of b over 2, that is the square of the sum, with the 2 on the outside, the square of the sum of x plus b over 2. Now that's a formula. I encourage you to memorize it, because if you do, it's going to make the completing the square problem a lot easier. Okay, so the square of x plus b over 2, what is that? That's the square of x minus 5. Yes, we have added 250 on the outside because we multiplied negative 10 by 25, which is the negative 250. And then the parentheses, inside the parentheses, is just going to be x minus 5 with squaring on the outside. Inside the parentheses, we have x minus 5 with the squaring on the outside. Negative 10 is out there. We have added those constants, the 6,000 and the 250, and we now have vertex form. And we are able to say that the vertex is going to be the point 5, right? The opposite of negative 5. Vertex is 5, 6,250. And so 5 is actually going to be the answer to the first question, and the 6,250 is the answer to the second question. The farmer should plant 5 additional trees and obtain a yield of 6,250 peaches. So I guess that would be the 25 trees and 250 times 25 peaches. We know that this yield is the maximum of the quadratic function, since the value of a is negative 10. Because it's negative, you have a max where that vertex is, not a min. Function opens downward, so the vertex must be a maximum. So there's your answer. How many more trees? 5. What is the maximum yield? 6,250. 6,250 is the max yield. Always remember to write the answer to a word problem in words. Now, if you're using the graphing calculator, you could verify this. So first you input the function, and you're going to need an appropriate window because, you know, with that 6,000 in there, that's not going to stay in the standard window. So I'm going to set my window to max out at have the top of the window at 7,777. And so we're going to have that parabola opening downward, and we're going to use a max feature to get an approximation to the coordinates of the vertex. Again, we talked about how it has a max, not a min, because the lead coefficient is negative. And the max feature works like this. You have to set a left bound on where you believe the max is. Now we believe, you know, we see this, we think the max is going to be right in there. That's where we think the vertex is going to be. Well, if we set a left bound on that way over here, we know that that vertex is going to be to the right of the left bound. We're also going to set a right bound on this vertex. We're kind of helping the calculator. You know, find this max. But that's a right bound on it. And so now we have a left bound and a right bound. The calculator knows to look for a max, a peak, a vertex between those two bounds. And so then we say, yes, go ahead and guess at the vertex. Calculator comes back and says, I think we've got it right here at the point 4.999981, 6,250. So the x value is obviously an approximation. Obviously, this number is extremely suggestive of the 5 that we got with our algebra, and that's the number of additional trees that you need. and 6,250 is the optimal peach production. Another problem, break-even analysis. The financial department of a company that produces digital cameras has the revenue and cost functions for X million cameras. So here they are defining X for us in this problem. X equals number of cameras in millions. And there's a revenue function, and like a lot of revenue functions, it's quadratic with a negative lead coefficient, right? That'd be negative 5x squared plus 94.8x. Cost function is linear, 156 plus 19.7x. That's a linear cost function. And both have the domain x between 1 and 15 inclusive. Now here's the definition of break-even point. Break-even points are the production levels in X at which R of X equals C of X. The revenue equals the cost. Then your profit is zero. You've broken even. If you produce more than that, then that generally means that you'll make a profit. Generally. Find the break-even points algebraically to the nearest 1,000 cameras. So X is in millions, so if it's to the nearest 1,000th, let's see, in millions, that's 6 places. 1,000 is 3 places, so we're likely to have 3 decimal places in the answer, 6 minus 3. Well, we're going to set the two things equal to each other. Revenue equals cost. That's how we find the break-even point. And we're going to do some algebra on that, just as we were about to do. We would certainly get rid of those parentheses and get everything on one side to solve this equation. So 94.8x, 94.8x, we've got a negative 5x squared equal to 156 plus 19.7x, and we're going to move some stuff. We're going to get everything on the left side. So we're going to subtract 19.7x from both sides. Subtract 19.7x. Subtract 19.7x. And we're going to add 156 to both sides. I'm sorry, subtract. Subtract 156. Subtract 156. That's going to give us 0 on the right. And on the left, we're going to combine these two terms, these two linear terms, to get 75.1 x. And the negative 5x squared is there, and the negative 156 is there. Okay? And we could solve that using the quadratic formula, with a equal to negative 5, b equal to 75.1, c equal to negative 156. And, you know, in your calculator, you want to be very careful. You know, the calculator probably forces you to put parentheses around the radicand, and you probably would do it with parentheses around the top, and you certainly want parentheses around the bottom. Or you could do some arithmetic by hand, but you get these two numbers. Now, that's not what happens generally. Generally, there aren't two break-even points. There aren't two x values, so that if you produce that number of millions of cameras, your revenue will equal your cost and you will break even. But it totally could happen. If you've got a quadratic revenue function, it could be equal to the cost function for two different values of x. So the company breaks even at x equals 2.490 million cameras and 12.530 graph confirms
million cameras.
That you get those 2 points of intersection if you graph the revenue function, right? You put the revenue function, here's r of x, you put that in your calculator. C of x is the line, and using the intersect feature, second trace 5, enter, 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 you get 1 point of intersection, and then do it again, second trace 5, use the right arrow button to move the cursor to the right, enter, 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 and you get another point of intersection.